Hi everyone. In this example you have to prove some inequalities, and we have two parts, part A and B. So this is part A. You have to prove this inequality, and you have x greater than 0 less than y. So you have to create a function and create interval, then you have to check the conditions of mean value theorem. So suppose that we have two numbers a and b such that 0 less than a less than b. So we have two real numbers a and b, and a is less than b, and both numbers are greater than 0. Now let f of x equals square root of x on the closed interval from a to b. Now you have to check the conditions of mean value theorem. This is the first condition. F x must be continuous on the open interval from a to b, and since we have square root of x and the domain of square root of x all real number greater than 0, so our interval have positive real numbers. So the first condition, f of x is continuous on the open interval from a to b. Now you have to check the differentiability. You have to check if f is differentiable in the open interval from a to b. So the second condition for M.V.T, you have to find f prime of x, and f prime of x equals 1 over 2 square root of x. Since we have square root of x in denominator, so you have to take real numbers greater than 0, and our interval is all real numbers greater than 0. The numbers inside the interval from a to b are positive, so f is differentiable. F of x is differentiable on the closed in the open interval from a to b. So the conditions of mean value theorem satisfied for this part. Now what's the conclusion? The conclusion is there exists C belongs to the open interval from AB such that f prime of C is equals to f of B minus f of A divided by B minus A. Now f prime of C is 1 over 2 square root of x. So you have to replace it by its value or its expression, 1 over 2 square root of C equals f of A, and f of B means square root of B minus f of A, which is square root of A divided by B minus A. Now in more details, we have C belongs to the open interval from A to B. This means if C is between two numbers a, b, then C must be greater than A and less than B. If you take the reciprocal of all sides, you will get 1 over C, 1 over B, and 1 over A. But pay attention here, when we take a reciprocal you have to change the sign of inequality. So less than here, it will be greater than. After that you have to take radical for all sides. So we have square root, square root, square root. Now square root of 1 over A equals square root of 1 over square root of A. So we have 1 over square root of A less than 1 over square root of C, and greater than 1 over square root of B. Now you have to multiply all sides by 1 over 2. So multiply by 1 over 2 for all sides, you'll get 1 over 2 square root of a greater than 1 over 2 square root of c greater than 1 over 2 square root of b. Now the middle term of this inequality is the same as f prime of c. So f prime of c is between 1 over 2 square root of b and 1 over 2 square root of a. Now f prime of c equals 1 over 2 square root of c and equals square root of b minus square root of a divided by b minus a. So now you can write this inequality: square root of b minus square root of a divided by b minus a is greater than 1 over 2 square root of b less than 1 over 2 square root of a. Now multiply all sides of this inequality by b minus a. You will get b minus a over 2 square root of b less than square root of b minus square root of a less than b minus a divided by 2 square root of a. Now change the variables. By changing the variables, you will get, if you suppose that a equals to x and b equals to y, you will get y minus x over 2 square root of y less than square root of y minus square root of x less than y minus x over 2 square root of x. And this is our inequality, and this is what you want to prove, and this is the final answer or the proof of this part. For the second part, you have to use the mean value theorem to prove that x over 1 plus x squared less than tan inverse of x less than of x for all values of x greater than 0. So as in part A, you have to create a function and interval, then apply the conditions of mean value theorem to this function on the given interval. So firstly, suppose a number or real number greater than 0, and let f of x equals tan inverse of x on the open interval from 0 to a. Firstly, you have to check the continuity for this function on this interval. So in part A, f of x is continuous on the open interval from 0 to a because tan inverse of x is continuous everywhere. The domain of tan inverse of x is all real numbers from negative infinity to infinity. So any sub-interval, tan inverse must be continuous on it. The second condition, you have to check the differentiability of this function on the open interval from 0 to a. So for part B, you have to find f prime of x, and this is the derivative of tan inverse of u in general equals u prime. The function here you have x, so the first derivative of x is equals to 1 over 1 plus x squared. No zeros of denominator. This function f prime is have domain from negative infinity to infinity. So in the interval from 0 to a, f prime is defined, which means that f is differentiable on the open interval from 0 to a. So the two conditions of mean value theorem satisfied for this function on the given interval. So what's the conclusion? Now the conclusion, there exists c belongs to the open interval from 0 to a such that f prime of c equals f of a minus f of 0 over a minus 0. Now f prime of c is given and equals to 1 over 1 plus c squared equals f of a means tan inverse of a minus tan inverse of 0 divided by a minus 0, which is a. Now tan inverse of 0 equals to 0, so you can cancel tan inverse from here, tan inverse of 0, and you will get 1 over 1 plus c squared equals to tan inverse of a divided by a. Now pay attention for this discussion. Now c belongs to the open interval from 0 to a. This means that c is greater than 0 and less than a. So I want this inequality, c less than a. So 1 over 1 plus c squared must be greater than 1 over 1 plus a squared, because 1 over 1 plus c squared have the denominator 1 plus c squared, but since c is less than a, so the denominator of this fraction is less than the denominator of this fraction. So this fraction 1 over 1 plus c squared is greater than 1 over 1 plus c squared. So if you have highest denominator, so the fraction will be increasing. If you increase the denominator, all fraction will be decreased. So we have this inequality, 1 over 1 plus c squared is greater than 1 over 1 plus a squared. Now this is less than 1, because 1 over 1 plus c squared is a fraction and the denominator is greater than 1, so it's a fraction less than to 1. So we have f prime of c, because 1 over 1 plus c squared is the same as f prime of c, is between the two expressions, 1 over 1 plus a squared less than 1. Now f prime of c equals tan inverse of a divided by a. So we can write that tan inverse of a over a is greater than 1 over 1 plus a squared and less than to 1. Now from this assumption, a greater than 0, you can multiply all sides of this inequality by the real number a. but you will not change the sign of inequality because a is a positive number. So you will get a over 1 plus a squared less than tan inverse of a less than of a. Now change the variables and suppose that x equals to a. You will get that x over 1 plus x squared less than tan inverse of x less than of x. So this is the inequality you want to prove, and that's it. Thank you.